So, talking about electromagnetic radiation, one of the forms we mentioned was radio waves. And if you have a radio wave of a certain frequency, FM 89.5, the 89.5 usually doesn't have the units written with it, but the units of FM radio turn out to be megahertz, capital M mega. Remember, mega is 10 to the positive 6 power. So that's the frequency, 89.5 times 10 to the 6th hertz. And in this question, we want to know what is the wavelength. So we're going to start from the equation speed is equal to frequency times wavelength. And if I solve for wavelength by itself, I can bring the frequency over to the left. So the wavelength is equal to the speed divided by the frequency. The speed is a constant, 3 times 10 to the 8th meters per second. And the frequency nu, 89.5 times 10 to the 6th hertz. And remember, hertz is also written as seconds to the negative 1 power. So that seconds to the negative 1 cancels in the top and the bottom. And we're going to get our answer in meters for the wavelength. And if we do this division, the wavelength lambda will be 3.35 meters. So that's a little bit of the background of what you need to know about wavelength and frequency. And now we're going to apply this to chemistry. On the right side, we have what's called a line spectrum experiment. And what we start with is a tube that's full, in this case, it's full of hydrogen gas, and then we apply energy to it. We turn on the power, and the lamp will light up, and we take some of the light, pass it through this slit that goes into a prism, and we break up the colors of the light. Just like here, we have what would come out of the prism from white light or from sunlight. You're going to get all the colors of the rainbow, Roy G. Biv, and this is called a continuous spectrum. Well, when we do this experiment in chemistry for hydrogen, we don't get a continuous spectrum. We get one line and another line, another line, and another line. And in between, we have a gap. So that's why it's called a line spectrum. And if we replace the gas in the tube with a different gas, then the line spectrum changes. So here we see the spectrum for hydrogen has very few lines. The spectrum for neon has many lines, and the one in the middle is helium. These are like fingerprints that you can identify what the gas is based on the line spectrum. So this actually caused quite a bit of trouble for scientists to understand why electrons only give you certain frequencies or certain wavelengths of light. Because remember, the wavelength and the frequency have a relationship to the energy. So if we only get certain colors of lines, that means we only have certain energies. And the solution to why electrons behave this way is a field of study called quantum mechanics. And the important result for us is that electrons exist in certain levels of energy. Sort of like steps on a staircase. If you add energy to the gas, the electrons will move to a higher energy level. However, they do not want to stay at the higher energy level. They would rather release that excess energy and return to what's called the ground state, which is the lowest energy level. So in order to get back to that lower energy level, the atoms must release energy Energy can't be destroyed, conservation of energy, remember. So the energy has to be released, and this turns out, for depending on where we're looking, and what we can see is just the visible spectrum, remember. So we see the light that corresponds to that release of energy.